All right, sports fans, welcome to your weekly SETI Institute colloquium series. Adrian Brown, who is MIA, asked me to do the introduction today because actually John Rather is somebody I've known for, I don't know, a longer period of time than it took for the Spaniards to settle the New World. Okay, let me just give you a little bit. We've got to get to John because he has a very interesting talk, but he gave me enough background information to form its own colloquium. I'll try and limit that to 1 minute, but he got his undergraduate degree in physics from the University of Tennessee at Knoxville, and then a PhD in astronomy from the University of California, Berkeley. I haven't heard of that place, but it's somewhere nearby. A fellow grad student was Jill Tarter, and his thesis advisor was Jack Welch. So there you go. Then he worked for 12 years at both Oak Ridge and Lawrence Livermore on, well, it was on plasma physics, and they were being told them, he tells me, that controlled nuclear fusion was only 10 years away. That's the story on controlled nuclear fusion. It's 10 years away and always will be. Then he took a job as a radio astronomer for 3 years at Kitt Peak National Observatory, part of NRAO, National Radio Astronomy Observatory. And that's how I met John, because he would occasionally come to lovely Charlottesville, Virginia, and we would commune there. He was thereafter recruited by a think tank, and their job was to look 20 years into the future. This was 1974, right, John? And it was to look 20 years into the future and decide what technologies were essential to the defense of the United States. And he came up with, he gave me a very short list of things they came up with. GPS, stealth technologies, precision guidance of missiles. I don't know what crystal ball you had, John, but whatever it is, you, I, and that crystal ball are going to Vegas. He then became vice president of an aerospace corporation. He developed adaptive optics. This, again, was for the Defense Department. But as people around here know, adaptive optics are on every major telescope in the world today. So you can thank John for that as well. Between 1990 and 1997, he worked at NASA headquarters as assistant director for interactive technology, worrying about asteroid threats and mitigation. You may notice that this week there have been no major asteroid impacts. I don't know if we can, thank you for that, but he, at this point, asked himself where he really wanted to be, and it was back in Tennessee, and that's where he is. He's at Oak Ridge, and he has formed a company called RCIG, which is Rather Creative Innovation Group, which, of course, is rather creative. And they're interested in energy storage and medical diagnostic technologies. Without any further blather from me, here's John Rather. You'd rather hear from him. I hope you can all use catalyze as a verb in 20 sentences.
Let's see, I probably have two microphones. Let me turn one off. There you are. After that introduction, I really don't have to say very much. I was told by Seth that this august assembly contains world's leading experts in various topics, and also people who have very broad interests, and people who are extraterrestrial freaks. And so it reminded me of the mother of the bride trying to plan the reception, and she said, well, shall we serve fruit punch and make the boozers unhappy, or shall we serve booze and make the abstainers unhappy, or shall we serve sherry and make everyone unhappy? So the talk that I planned, I was very eager to come here because I trace my origins all the way back to Frank Drake's initial OSMA project, which got going in about 1958, and I was nearing the completion of my physics studies at UT, and OSMA was in the press, and so I dropped everything, wrote a letter to Frank, and said I think I was going to graduate school, but I'd rather come and work with you and discover extraterrestrial intelligence. And he wrote me a very nice letter back that I still have that said, well, it's probably going to take 10 years or more, and why don't you go on to graduate school first? And so that straw in the wind got me involved with SETI, and then as Seth mentioned, I knew Jill and Jack quite well, and one thing's led to another. I've evolved in many different directions, but I still have a great love for this effort, and think that the people that are carrying the torch really deserve a hand themselves. And so this was the original name of the talk, and I'm going to actually discuss this. But more generally, in the context that I was just describing, can Earth qualify as extraterrestrial intelligence? And if not, what do we have to do in order to qualify? And that's the real subject. So my topics, I'm going to start with a very brief commentary on SETI and our current perspective on it. And then I'm going to talk about how developing the solar system, getting a human presence off the Earth and into the solar system is really the first step. We aren't even there yet. And how von Neumann engineering can really be the key to it all. If we can use small near-Earth asteroids and develop von Neumann engineering, then we have a building premise that can lead to all kinds of new opportunities, including how to launch ultralight interstellar probes. At the end, I want to come back and visit the SETI context again and try to tie things together there. But I do shotgun around, and it sometimes works and sometimes doesn't. An underlying fact is that right now, macro transformative technologies are really trying to happen and moving much faster than people may know. Particularly high temperature superconductors are really going to change the world in this century, and they lead to super powerful magnets and machines that are nearly 100% efficient. The most common example of superconducting technology, of course, is MRI machines in thousands of hospitals, but then the superconducting technology at the Large Hadron Collider, the most advanced system in the world, I think, is another extreme example. Magnetically deployed huge structures can result directly from high temperature superconductors used in a new way in space. I want to talk about that. And it makes possible ultra lightweight self-deploying devices. It also pertains to electromagnetic launch from the surface, and you might want to go on the web and look at StarTram. I've been very happy to be working with Jim Powell, the inventor of superconducting maglev, for many years, 35 years, and we came up with the StarTram idea. There's now a very good book on it that pertains very much to interstellar travel as well as other things, and I advocate looking at that. And high energy lasers, another part of my career that are also happening now. It's taken a long time to get well-controlled high energy, but that too has big implications. First, just a few remarks about the present SETI status, and of course the Drake equation is the heart and soul of it. I saw this out on the welcoming desk, and so it's enshrined in metal right here. My son, Rick, is a robotics expert at Texas Instruments in Dallas, and he also loves SETI and has for all his life. He wrote a nice program that you can input any entry that you like and get the following result. The number of stars in the galaxy is pretty accurately about 1 trillion. That's our galaxy, the Milky Way. The fraction of stars with planets, the next 4 items, we've learned so much in the last 20 years that these are good numbers, that 100% probability, I think, that most all stars have planets, and at least one in the life zone. And based on what we are learning ever more every day about bio origins and genetics and everything else, it's quite reasonable to believe that every planet in the life zone will develop some form of life. And given a few billion years, 3 billion years like on the Earth, you can assume that some of them will be intelligent life. And so it makes these things that were very indefinite at the origin of the Drake equation pretty much in the bag now, I think. Still, the fraction that can communicate is very debatable. And looking at the billions of life forms that have been on the Earth since the origin 3 billion years ago, there is only one that we know of that is actually to the point of communicating. The other most intelligent creatures are dogs and elephants and porpoises and octopi and perhaps million occupant anthills. And so we can assume that there's a lot of life out there, but whether it has the resources, the planet is agreeable to technological development is quite another matter. So I give it once in a million there. And the lifetime, the most troubling one of all is the lifetime of communicating civilizations. And in view of how far we've come in 10,000 years and how we're verging on disaster right now, I think suggesting 100,000 years based on our experiences is generous. Well, putting these assumptions together, the number of communicating civilizations that you can expect in the Milky Way galaxy now is about 20, and that means that the average distance between them is on the order of 32,000 light years. And so it's pretty daunting and even worrisome, but at least it provides a basis for thinking about it further. The other SETI issues that I'm going to come back to at the end of the talk have to do with the Fermi paradox, the absence of evidence, the zoo hypothesis, and the robotic threat, and we'll just mention those briefly toward the end. Steps to the stars can start, I think, with near-Earth asteroids, and the idea here is that can leverage development of the solar system and get the human race off the planet and into permanent habitats in interesting places. In order to do that, we need synergistic, integrated macro projects, both in the near term and far term. And I'm going to talk about asteroid capture and industrialization, implementation of safe human travel, safe lunar colonies and industrial development, and Mars and Jovian satellite travel and development. The NEAs, 10 meters in diameter, can provide useful materials that are easier to get at and easier to industrialize and engineer than moon dust. You don't have to get it from the surface of the moon into space. I want to talk about that. Very important is that asteroid dust makes great radiation shielding, and 2 feet of it around a occupied habitat gives you as much protection as the Earth's atmosphere and solves the problem of cosmic rays and solar flares. They can also give you free rides to low Earth orbit and the Moon and Mars by launching them into orbits or finding naturally occurring ones that osculate the orbit of the Earth and Mars, or putting them into figure 8 orbits between the Moon and the Earth to transit through the Van Allen belts. And angular momentum pseudogravity is easy to achieve too. So we need these synergistic integrated macro projects both in the near term and far term, and want to talk about how to do that. Most of you saw the Chelyabinsk incident a couple of years ago on Google, I imagine. Has everyone seen the impact into the atmosphere of an object traveling, I think, at about 20 kilometers per second? And it disrupted about 40 miles from Chelyabinsk with a yield of something like 20 megatons. I don't remember the exact thing. That was a very high velocity encounter. But if you define a sphere the size of the moon's orbit, 10-meter objects are extremely common, and they're very hard to find because they're too small, and you can't find them when they're far away and they just pass by in a few days. But now and then they do pass through the Earth's atmosphere. One of my favorite pictures, this is an old one, of a 10 or 15 meter diameter asteroid that passed 40 miles above the Grand Tetons in 1972. And it was slow enough so that a lot of people with old movie cameras were able to photograph it. It was in the sky for a couple of minutes. And hey, by the way, the Air Force even then had missile detection systems in space, and they measured the deceleration of the thing as it was passing by and knew its altitude, and so they were able to estimate its size and mass. And it's a very good example. Every couple of 3 years, there's usually an impact or a disruption of a thing this big in the oceans primarily, and you don't hear about them. We learned a lot more about asteroids in the last 20 years or more, and this image of Eros is particularly nice from the year 2000. It's a fairly big one. It was the first near-Earth asteroid discovered maybe 70 years ago or more, 80 years. It's interesting, these pictures, because you can see that there was an impact on the bottom side that blew out a lot of stuff on the other side and deformed the whole thing. It's about 12 kilometers long, I think, and it's pretty evident that it's kind of loosely aggregated material. As the lander approached Eros, this picture from a kilometer away shows the dust, and you can assume that a lot of these very small asteroids that pass near the Earth have similar composition. So I already mentioned the dust from these things can solve the radiation problem for humans in space, because 60 centimeters of it provides the protection of the Earth's atmosphere. Now the question is, if we're going to capture them and use them, how can we do that? And I think the very important hint comes from knowledge of the natural evolution of asteroids in the solar system. This slide is probably 20 years old. It's the first 5,000 detected asteroids, and you see Mercury, Venus, Earth, and Mars in here, the asteroid belt, and then Jupiter out here. If you look, the points up here, ignore the little V's, those are comets coming from all directions, but there's a cluster of asteroids here and here that are called the Trojan asteroids, and they are, Jupiter is 5 AU out, they are displaced like a triangle with respect to the location of Jupiter and synced in orbit. But the point is that the velocity of these things with respect to Jupiter is practically zero. Well, a few years ago, the same thing was discovered on Mars's orbit, and there are a few of them that have been identified there, and there's every reason to believe that the same is true on the orbit of the Earth. Lagrange points have been known for 250 years from the French mathematician, and when you have a planet like the Earth, the L4 and L5 regions on the orbit are where you go to look for these things. But remember, the Earth is 1 AU out, and so you have to get detection systems over here where you can find the zero velocity candidates and then tweak them so that you can bring them back. And it turns out you have L4 and L5 points on the Moon's orbit around the Earth, and so you can bring them back to those regions where you can work on them and engineer them. The three essentials are to find them and get to them, and then deflect them or tame them one way or another. The detection thing, the only way to do it is with infrared, and satellites inside the orbit of the Earth are appropriate for this kind of thing, maybe on the orbit of Venus or so, looking outward, and as they scanned across the L4 and L5 orbits, you would catalog them. Then when you have the ability to tweak them and bring them in, you can evaluate the materials and do more with them. I'm going to skip over the part of that because we're a little bit late already. The capture method that I'm going to propose is something you may not have heard about, but I think it's very important. The fundamental experiment was done by Ampere in 1835 and repeated by Michael Faraday. You flow current down a wire from a battery, and back up the other side, the wires bulge apart because the magnetic fields are opposed. And that means that it wants to spring out and form a perfect circle. And it really works, and when it does spring out that way, the plane that it defines is really good. If the wire is supple enough so that it doesn't distort it, you get a really flat surface. Well, if you do this with superconducting, high temperature superconductors, which are coming on strong now, this is a very easy way to make very lightweight structures that can be huge and formed any way you like. We call this MIC for magnetically inflated cable, and it's a transforming technology that can produce solar concentrators and light sails and huge telescopes. And initially we were looking at the all three. We published a paper on this that's available. The original ideas were, how do you develop a telescope that can look at planets around nearby stars and really image them and diagnose them carefully. And what you have here is a 1 kilometer diameter system with the MIC wires out here that are pulling out the fibers, and that defines the membrane here, which you can engineer in such a way that it's good enough to do imaging, compared with the Hubble and the James Webb and the Keck and the Magellan telescopes down here. You see, we're talking big stuff. The thing that I want to focus on, though, is the use of it for a solar concentrator, and the object is to capture 10-meter diameter near-Earth asteroids and bring them here where we can use them. And you do the same thing. There's a superconducting ring here and one out here and one at the rim of the membrane. And I can show you, this is the payload from a rocket. It happens to be 12 feet in diameter, just like the SpaceX rockets. And this is the package that you deploy. Now you see the two rings are repelling each other, and there's a conductor all around the outside of the membrane, and so it spreads out, and you can see how you can pack a very light payload with the proper fibers and so on to bring it to shape, and there you are. The next thing you can do with it, that's a focusing solar radiation, but that ring there is inside the focus, and so it's pretty hot but not too hot. And that means you can use a monopropellant to steer it and displace it to where you want it. And this shows that we're coming up to one of our victim 10-meter diameter asteroids. And you turn the asteroid itself into a rocket by evaporating away the surface. So if you can track it for a reasonable amount of time, then you can snag it. And we've done the numbers. By the way, all the stuff I'm talking about, we have a lot of technical detail, but I couldn't put it here. I did want to mention this particular data here. The required delta V to trap and move the thing, if it's 1 kilometer per second, then you need this 5 times 10 to the 12th joules. You would evaporate 365,000 kilograms, which is a volume of about 146 cubic meters, and that leaves 3 times as much of the original stuff with a mass close to 1 million kilograms. And it would take about 5 days for the reflector to do that. And I assume that you're going to find a bunch of them at the L4 and L5 points with no more than 5 kilometers per second delta V required. And so somewhere between 5 and 15 days should do the trick, and you'll come away with still thousands of kilograms, hundreds of thousands of kilograms of useful material. I want to mention in passing, because it pertains to the lifetime of intelligent civilizations, we all know now that 65 million years ago a big one hit, and I think that the threat from comets is much more serious than asteroids. We're getting very good at cataloging all the asteroids, but the comets come out from deep space from the Oort cloud. We don't have much warning, and having terminal defense against it is really, really important because it can happen. And I chaired at Los Alamos in 1992 for the Congress of the U.S. The first study of the mitigation of the impact threat, what to do about it. Of course, everyone was thinking, well, you could just nuke one of them, but there were immediate protests about even thinking about that. And so we came up with, at that time, the Star Wars effort was still going on, and brilliant pebbles had been proposed using little kinetic interceptors to destroy rockets. We came up with brilliant mountains instead, where we would move a family of these 10-meter objects into the incoming path so that they were within the target zone. And if the comet strikes any of them, the yield that you get at cometary velocities is many megatons. And there's a very convenient mnemonic that you should remember: 3.5 kilometers per second impact of anything with anything releases the same amount of energy as the equivalent mass of TNT. And so since kinetic energy scales as the square of the velocity, if you go to 7 kilometers per second instead of 3.5, then you release 4 times as much as TNT, and so on up. And since comets can be up to 70 kilometers per second, you're into nuclear territory pretty quick. So in terms of prolonging the lifetime of the race on this planet and keeping civilization going, I think it's worthy to think about what you can do with asteroids just for defense. And some of you no doubt have seen the impact of a 370 kilogram copper ingot on the comet Tempel 1, which blew a crater about 100 meters in diameter, but that was a proof of the principle. The relative velocity there was about 5 kilometers per second, no, 10 kilometers per second, I'm sorry, it's right here. And you can see down here the 10-meter asteroid, mass of about 500,000 kilograms, meeting a comet at 40 kilometers per second, is equivalent to 75 kilotons of TNT. For space travel, what you want to do is snag these things and hollow them out and make them nice and comfortable on the inside. And if we take a pair of them and put them 500 meters apart, revolving by cables at half an RPM, that gives equivalent to Mars gravity. So you're solving not only the radiation problem, but also the problem of long exposure to 0G. And this shows the 2 asteroids that have been modified appropriately, connected by carbon filament cables with their solar cells and the windows to look out, and a long tube connecting the 2 of them with the Mars lander here in the middle. And let me hope that this one will animate. And it looks like it's a lot more fun than being cramped inside something shaped like an Apollo capsule or something along those orders. So now these are all, I view them as fairly near-term things. If we exploit the deployment of these structures with superconducting magnetic technology, then these things could be done in 10 years if we decided to do something other than send astronauts out to watch a robot snag an asteroid and bring back a rock. I think that this would be could be accomplished for the equivalent amount of money and might lead to more productive things. But to really industrialize them and to develop the solar system is the next step. And how do we do that, and how does that get us to the nearest stars? Von Neumann engineering is what we're talking about, and as I said, I meant to mention anyway that John von Neumann, a Hungarian immigrant who came over just before World War II and was at Princeton for a long time, proposed machines that could manufacture replicas of themselves. And of course, this idea is in science fiction everywhere and has been around. It was kind of fundamental to 2001 and 2010 and so on. The black monolith repeated itself on Jupiter and what have you. But we get a new take on it now, because what I think is that hierarchical synergy is very powerful, that tiny machines can beget giant projects. And that means we want micro to macro von Neumann machines to become reality. And so I want you to think about how we can develop those initially to colonize our solar system and then evolve the same sorts of technologies for interstellar transfer. The micro transformative technologies are really coming on fast too, and as many of you know, they're near the state of the art. MEMS is everywhere, micro electromechanical systems, and three-dimensional printers. And the point is, you can start thinking about very tiny three-dimensional printers that can print bigger things that then print bigger things and so on. So we need to demonstrate the tiny first-generation devices now that can progressively build larger next-generation machines, both individually and collectively, so they exponentiate in space. And I think that these are perfect candidates for academic scale work right now. We can start parallel development projects with modest funding and demonstrate transformative things. A fellow I was talking to here before the talk began is working on small satellites, and this is the kind of thing that academic groups could build and launch to demonstrate. Then, assuming that we could use that to industrialize the moon and industrialize asteroids and get us permanent colonies on Mars and the Jovian satellites, then how can we progress to interstellar launch? And for this, it's really a daunting problem, and I've been forced to think about ultra-lightweight interstellar probes. The reason is that the stored energy required to accelerate just 1 kilogram, 2.2 pounds, to 3% of the speed of light, which ain't very fast by interstellar standards, requires 10 to the 14th joules, which is 100,000 gigawatt seconds, and that's assuming 50% efficiency. The total generating capacity of the United States is about 1,100 gigawatts, and so it could launch a kilogram in 100 seconds if everything in the country were stopped and all the power were put into that for 100 seconds. The 100-meter diameter solar concentrator, however, that I was showing you earlier, in space provides 10 to the 12th joules per day. So it requires about 200 days to launch the 1 kilogram. You can think about automobile racing, where if you want to go from 0 to 200 miles an hour on the straight, you need about 1,000 horsepower engine. But if you don't care how long it takes and go around and around a track, a 10 horsepower engine will do, just so you keep accelerating. And so it's the same general idea. Well, of course, that's what's done in the Large Hadron Collider, and you have 1,600 magnets that accelerate protons to the 0.999 of the speed of light. They make 11,000 orbits around the 27 kilometers. total distance of 300,000 kilometers in a second. And so you start asking, well, why can't we do the same thing to launch interstellar stuff? The trouble is this is for one proton, and there are a heck of a lot of protons in 1 kilogram. And so as you add to the mass, the centrifugal force is greater and greater, and you get well beyond the ability of these superconducting coils to contain it. However, there are people like John Mankins and Jim Powell who are undaunted by this, and they realize that if you go to a large enough radius away from the planet, that you get to the point where the centrifugal force can be anchored by a string of my engineered asteroids, which you see here, one here and one there and off into the distance. And these actually have to be about 10,000 kilometers apart with the superconducting ring going around it and the launching craft riding on it. And so each of these has the power supply and adds current to the superconducting ring. So over a period of 200 or 300 days, the craft tracking with it gets up to 3/10 of the speed of light. Let's try once again for one of my animations. And you wouldn't see that curve, but you see the thing slinging off. And of course, that picture was taken in about a 10 millionth of a second, and so we're a little light starved there. The travel time at 3/10 of light speed to Alpha Centauri requires about 160 years, including the time to decelerate. It doesn't do any good to launch something that's just going to fly by there in a few hours and is gone. And the question of how do you slow it down is a very tough question. Actually, the last time I talked here at SETI was 25 years ago, and I was advocating the importance of lasers then, and what you could do with high-power lasers. And as I mentioned, they are coming on strong now. This was published in the JBIS, what was it, in 1991. But a very important point is that just for SETI itself, in the early days, lasers were rejected because it was thought that the photon noise of high frequencies would kill it compared with the radio SETI. But we realized that you don't require a heck of a lot of laser power to go a long way. This is distances out to 10,000 light years if you concentrate the power on the life zone around the star. And so you're not broadcasting power into 4 pi steradians, you're focusing it instead. And then very modest optical sizes, 10 meters, which we can build now, or 100 meters, which are coming up in the next few years, can develop high signal to noise at great range. And the starlight from the star, our star, the sun, is decreasing with distances inverse square, but the laser light is not. It is within the focal range, the Fresnel range of the transmitter. And so you maintain high signal noise. This made the same principle that optical fibers give us the very high speed internet that we've got now, you see. So I was thinking von Neumann machines even then, plant them on Mercury, and they, over a period of time, turn Mercury into a giant laser and telescope. It's got interstitial photoreceptors and light-emitting diodes, coherent ones, and so it's seeing all the dark side away from the sun as Mercury goes around the sun. And it can see every star in the galaxy, and it can tailor a beam that is transmitted to it. Well, this Bob Ford and I got into some interesting discussions of just propelling light sails to the stars using this kind of thing, and it can be done. Omni was popular in those days, and they picked up on the idea because I suggested that this was the way to transmit the human genome. And so laser clones is what attracted that. Well, transmitting the human genome at light speed is just fine if you can persuade a SETI friend to build a receiver. And the only other alternative is to first send the receiver there by a covered wagon, and the covering is the membrane that's going to decelerate it, because the payload we're talking about is 1 kilogram. We need about 20 kilograms to accommodate the deployable membrane that has a very important function. If we had only the payload flying along, even though the interstellar hydrogen and other stuff is pretty rare, maybe 10 atoms per cc, you're sweeping out a very long, narrow tube, and so the payload would have radiation impinging on it the whole way, which would destroy everything inside it. However, if you have this superconducting ring with the membrane, as is well known in a lot of physics experiments, the membrane will ionize everything that passes through it, and then the magnetic field will sweep it away so that it doesn't impinge on the payload. And at the same time, of course, it's exchanging momentum, and so it's decelerating the payload all the way from here to where it is aimed at. And if you choose the size and so on, just so, it'll arrive at a nice pedestrian speed where you can trap it in orbit around the planets there. Thin membrane stretched by magnetically inflated cables solve two major problems for interstellar transport. They ionize and deflect interstellar particles to eliminate radiation hazard, and they provide gradual deceleration through the coast phase. The next question is, well, if you're going to launch things like that, what's the payload content? And the initial hierarchical robotic von Neumann machines go to prepare a way for the real payloads. They make thousands of little habitats and incubators and laser data receivers on the candidate planet. And then the real payloads are then launched, which deliver many super von Neumann machines with initial weights of 4 times 10 to the minus 6 grams each. And fortunately, every woman on Earth knows how to produce these about once a month. And they weigh about that, and they're about 1/10 of a millimeter in diameter and have about 10 to the 28th components. And obviously, if we've put down on the planet a nice creche and robotic nannies to receive these things, then we could, in the next 100 years, probably reprogram the emerging human by transmitting laser information about our genome, so each of us can be replicated on the other planet and go on and party. It's, you know, the males are in this too. They're kind of cluttering up the scene here, but you can ignore that. Now, I want to return finally, time's about up, to the SETI context again, and wonder how all of this speculation might play. I think the heart and soul of the question is the Fermi paradox, and I imagine most of you know that during the Manhattan Project at Los Alamos during the war, Fermi, Enrico Fermi and Edward Teller were having lunch one day, and Fermi said, you know, if there are extraterrestrials, they should be here already, because even traveling at a tiny fraction of light speed, they can be everywhere in our galaxy within 100 million years or less. And so where are they? And the question remains. It's a very good point. I think that pondering the issues surrounding von Neumann reproduction helps us to look at those questions. The largest uncertainty, as I said before in the Drake equation, is the lifetime of technical civilizations, and exponential human reproduction is now verging on a crisis. The population explosion is still with us. India is now expanding at greater than one Australia per year, and Africa is still doing the same. And so we have some stuff going on the Earth that is really taxing the system, and we don't know where it's going to lead. So I think the next 2 centuries will determine whether we can go to the stars or we're going to self-destruct. And there are a lot of lessons in that. You see an evolution in science fiction now, ex machina even recently, that, well, we're pretty bad and pretty soft, and yet robots are more enduring, and we don't need to go there. The robots will do it for us, and they can replicate themselves, and so on. I tend to be a little bit skeptical about that, because I'm not sure where human consciousness and where concepts of morality and other things come from, and I'm not sure whether machines will develop that on their own. They may just exponentiate themselves and devour all of the resources that are available to them. So I think that if human-like or robotic von Neumann life expands rapaciously, it's probably going to self-destruct on its parent planet or solar system, or maybe if it starts to expand beyond it. Hence, logic-mediated altruistic life is more likely to survive and expand through the galaxy. And if that's the case, then the logical conclusion, I think, is that either we are alone in our galaxy because they're not here, or they are already here and they're clandestinely waiting to determine whether we're going to be nurtured by them or destroyed, just to see what are our motives. And I'm afraid we're stuck with that, and so thank you very much.
It's the usual custom here that the person who introduces the speaker asks the first question, but that violates Emily Post's norm, so I'm not going to do that. I'm going to let you ask the first question, who would like to do so. And I have to get this microphone to you because of the many viewers of this colloquium online. So who has a question for John? Bill.
John, that was a very, very interesting talk. I hadn't heard that you could inflate something with a couple of copper cables like that. But clearly people were trying to build sails, large sails in space. I don't know that they use that, do they?
No, they don't, and I think they should be, because it enables very precise structures. And you mentioned copper, but they don't need to be as heavy as copper. There is a tape that is metallic, and the high temperature superconductors which can be passively cooled in space with the proper super insulation around them to 50 degrees Kelvin, 20 degrees Kelvin. And so it's the pretty low mass material for the purpose. But the fact that once it's out there, there's close to 200,000 amperes flowing in the rings, and so the stress is tremendous, and it stretches the membrane very tightly. And I've wondered, you know, right here at Ames at Moffett Field, the very first communication satellites in the summer of 1962 were inflatable spheres and echo balloons, and they were 100 feet in diameter, and they did just fine. I was living in Oak Ridge back then. We were painting our house, and every 2 hours we'd turn out all the lights, and all the people painting my house would lie on the grass watching the two echo balloons come across. One night they came so close the images merged and went apart, but it worked, and that's an example of how you can have something that you could do light sail experiments with 50-year-old technology, 60-year-old technology. And I don't know the answer to your question, but
I think you're saying that the technology hasn't been proven, otherwise people would use it.
That's right, but we can prove it in, it was proven by Ampere in 1835 that it works. You know, it expands wires.
I don't think he used superconducting conductor
No, he did
resistance.
not, but that makes the case even stronger, because he used the power of a battery, you know, and was able to measure it. And So we're talking about big stuff with high currents that is that much better, and so that's about it.
Other questions for our speaker? Let's make sure I go back and forth here.
Thank you. So one of the things that affects all spaceships is the technology is kind of frozen at the time of launch, or actually the time of planning and building it, even before launch. And so given the, we'll take like a 160-year trip as read, and a lot of more technology happens in 160 years here on Earth than is going to be happening up there. So have you given thought to upgradable ships? Because if you can communicate with lasers some sort of at least software upgrade or new sets of instructions that could cause it to build something that would then be able to take the software upgrade in flight?
It's a really nice question and very good one. If you think of the membrane that I was describing as the decelerating membrane and to prevent radiation, it can also be concave looking back to the Earth, and that means that it can focus the laser light that we transmit from the Earth to have the upgrade information. And so in principle we can be upgrading during the whole time. And 160 years at 3% of the speed of light, you're right, a lot of upgrades. And so the von Neumann nature of the machine that you're launching needs to be adaptable to that, so you can tell it what you want it to do in the best possible way.
What do you say to people who say, look, 5 years after you do this, there'll be a 5% of the speed of light spacecraft that'll overtake this and make it irrelevant?
Oh, well, this is great, and I think all of science fiction is predicated on things that skip beyond what's been proven already, and including Kip Thorne's work in Interstellar and so on. And maybe we can engineer wormholes, and maybe all of this is just very unfortunate, primitive discussion. But Robert Heinlein wrote a book many years ago. What was the name of it? It was about the twin paradox. But the twins could communicate by telepathy. One of them went to the stars and the other one didn't. And the only thing that sustained them getting to the nearer stars was, of course, that the twin on board was aging much slower than the one on the Earth. But they got to the planet and they were having a lot of trouble with the native life forms, killing them. And the Earth sent out the new probe that arrived in 5 days to rescue them because of the progress that had been made. Yeah.
Other questions? Yes.
If you send an ovum and it develops somehow, how would it ever learn to do anything? I mean, even if the only way I can imagine it would ever grow up, being that babies are so helpless, is if it fell into a advanced civilization, which probably wouldn't be amenable to humans taking over.
Of course, I was talking largely in tongue-in-cheek, and I hope I didn't offend anyone in the process. But I suggested building a very appropriate creche with all the toys and so on that are needed to grow up, and having robotic nannies to look after things during the growth period, and no doubt sending TV to entertain them as children, and what have you. So as far as reprogramming our genome into a growing human, well, that's a real reach, and probably they would just be programmed by artificial insemination, when they arrived, and you'd take what you get, the usual crapshoot, So I won't stick my neck out and try to defend any of the details of this.
This side of the room is uncharacteristically taciturn. Is there nobody here who...
They're bewildered,
Yeah.
Thank you. I had a question about the size of the sail. So it would be, if it was a kilometer the kilometer in size, that membrane, once it's inflated, wouldn't that increase the probability of it getting struck by other projectiles in space? And what would be a way of mitigating that damage?
Yeah, the sail, I don't exactly call it a sail, but the membrane itself would be supported by a cat's cradle of fibers that are what define the ring and the shape of the thing. If it wants to be a parabolic surface that could focus the laser light from the Earth. So it isn't completely vulnerable in the sense that you expect it to be punctured by occasional either large atoms or grains of dust. And I did a lot of work on interstellar matter when I was still an astronomer, and it's pretty darn rare, particularly in the local neighborhood. We live in kind of a bubble that doesn't have much here, but the main thing to worry about, I think, is hydrogen and helium, which are the two most common things in the universe, and they are atoms, and they're just going to be ionized passing through. And the rare possibility that something massive might hit the superconducting ring, well, sayonara, you know.
Thank you.
Yeah. Anybody else?
Back to the zoo hypothesis. Assuming the aliens are here, waiting for us to either kill ourselves or mature enough to be worthy of contact, how would you go about searching them out right now?
Very important question, and I don't know. I think the SETI Institute is much better equipped to answer that question than I am. I know that people have been expecting to find the evidence, starting with Roswell, New Mexico, and working up from there. And I just don't have any way of answering the question except that we can assume that it's a very, very advanced civilization, whatever it is, and that they're pretty good at stealth and concealing themselves.
Take another question or two? Yeah.
Yes, your deceleration membrane / radiation shield, it seems to me it won't protect you from cosmic rays because they come from everywhere and they'll be coming into the probe all the time.
This is a good point too, and you're right. The fact that the payload is small helps a lot, and the fact that really energetic cosmic rays that can get through a reasonable amount of cladding around it is pretty scarce, and so again it's kind of a statistical thing. We know from myriads of satellites that have been launched for 50 years now that some hits occur and sometimes they disturb the electronics, and we know how to build electronics that can work around it and so on. But you're right, it's a crapshoot again.
Elliot.
Thanks. It seems that your spacecraft propulsion communication technologies are very much more advanced and proven than the von Neumann machines that are still seem a long ways away. Can you speak to the difference in development and why you have confidence in self-replicating machines?
I don't think it's that far away. I think that the pieces are lying around, and that it just requires some new think to how do we put them together. And I think right now the people working on three-dimensional printing need to think about what is the smallest three-dimensional printer that we can make that can make something bigger, and including the microcircuits and stuff that need to go with it. And so it has to be thought about in terms of what is it we're actually trying to build, and what is the kind of minimum complexity of the fundamental first thing in order to get to the bigger things.
Hello, John.
Hi.
I was a graduate student at Kit Peak when John was doing a lot of cool stuff. One of the things on propulsion that I didn't hear you talk about is some sort of compact nuclear. if you can convert, fusion is a few tenths of a percent efficient, and fission is not too much worse. Why do you need some giant planetary engineering thing when it might be easier to do a compact nuclear propulsion system?
Yeah, I've been attending meetings on this subject. The Tennessee Valley Interstellar Workshop meets every year or two, and we've had a large number of people come and talk about the Icarus project. And one thing on that, it's a little bit aside from that, but a lot of people hand wave and say, oh, we'll learn how to do annihilation of antimatter, and that'll solve all our problems, 100% efficiency and so on. But Jim Powell, who is one of the greatest physicists in our country, still at age 83 now, is the co-author of the book Star Tram that I mentioned. And it's a devastating treatment of that, because it turns out that the muon flux from the annihilation is such that where you're annihilating has to be about 10,000 kilometers from the spacecraft. And so there are a lot of problems with it, and not to speak of the problem of making tangible amounts of antimatter. But yeah, now I'm coming to that. The same book, Star Tram, also discusses 3% efficient fusion, and the Icarus advocates have been looking at doing that. And it's still monumental engineering, huge, expensive. The estimates of the cost of building the spacecraft and so on are trillions and trillions of dollars. Now you get back to Freeman Dyson 40, 50 years ago, and the ideas back then, wouldn't it be nice if we could get rid of all the nuclear weapons and use them for propulsion against a plate? You know, you disgorge a bomb and it goes off a kilometer or so and detonates, and it was called the Orion project, and it can work. It's one way of doing things, and there are other very interesting things that have been kind of lost in history. A guy at JPL 50 years ago pointed to the importance of staged nuclear propulsion. That just as we got to the moon by having 3-stage rockets, if you have a big one and a smaller one, then the benefits add up. And I think he came up with about a 10-stage nuclear rocket that could get to Alpha Centauri at maybe a tenth of the speed of light at most. But there are other possibilities out there. But I think with the present ideas of no new taxes and so on, that the chance of funding any of them is pretty remote. And I've been trying to propose things that I think can be done and can work kind of within the framework of the existing space programs and the motives of NASA and SpaceX and the others.
All right. This clock on the wall behind us is in a relativistic time frame, so it's running slow.
Yeah.
I want to thank our speaker, John Rather, and we have this SETI mug here that'll
great.
impress your colleagues. Hold things down on your desk.
Thank you.
I think we should give John a round of applause.